Hi everyone, this is the last video of the multi-asset mean variance optimization video. If you haven't seen my previous videos, please refer to my channel. This will be going into the last part of the R code that's necessary. So for 506 students, this will be helpful for finishing up the project. We'll go into some of the forecasting and regression techniques that are necessary for the last part of the project. So at the end of this video, you should be able to complete that. For those of you who are using Excel for the project, I'll have another video uploaded very soon, ideally in the next few days, but that'll depend on whether or not I'm able to complete the video and editing by then. But for now, just know that per my announcement, if you are using Excel and you have questions, I'm available for office hours or individual meetings or anything that you need. So yeah, just going ahead and continuing with the work that we did on the previous one. So in the last video, we ended on the portfolio index. Uh, and as we can see, right, this is where we ended. We had the graph of the portfolio index where we invested in 5 stocks versus the S&P 500. So now in this video, we're gonna go into the hypothesis testing. So seeing whether the variances are equal, the returns are equal of the market portfolio versus the portfolio of our stocks. We'll make the security market line and graph that, as well as doing a regression analysis on it. We'll go into the comparing the portfolio return premiums, the portfolio risk premiums, this should say, with the market risk premium. And we'll go into the dummy regression with COVID, value at risk, and we'll end with forecasting. So the whole winter forecasting that we've begun to get into recently. So diving right into it, the first step, once we've finished everything before this, would be calculating the security market line. So we already have a column of portfolio returns. And again, this whole code, the R markdown file, this Notion file, this will all be in the description. So if you're looking for any materials that's in the video, please refer to that. So yeah, we'll calculate the security market line, which uses the return premiums. So these will be the difference between the returns for each period, right? Each month that we're using will have a return, which is the combination of our weights multiplied by the returns of the individual assets. And you're subtracting the risk-free rate from that minus the risk-free rate. So the risk-free rate, this was defined previously. This would be the 10-year bond price values, and those would be divided by 1,200 to adjust for the monthly returns for a bond. So this formula is a little bit different from calculating the returns for the other ones. Just keep that in mind. So you're subtracting the risk-free rate from each month's returns, putting those all together in a data frame, and then this just shows the data frame. We're actually calculating the regression in this step, and for that, we use this formula. So LM, summary LM, and this will be the Y variable, and this will be the X variable. And then we get the coefficients that will ultimately tell us whether this will tell us the portfolio beta, the alpha, the intercept, and whether they're significant. So if the alpha, the intercept coefficient, is significant, you can see that with the p-value. If it is significant, that means the returns are not explained by the market, or the returns are abnormal. But if the p-value is greater than the alpha, then we know that the returns are explained by the market, so they're not abnormal. The market return premium or the market risk premium estimate. That will tell you the beta for the portfolio. And then the p-value will tell you whether it's significant or not. So since this p-value is less than 0.05, which is our alpha, that corresponds to the 95% confidence level, we know that the beta is statistically significant. For graphing the security market line, I'm just taking the market risk premium, the portfolio risk premium, these columns from the security market line data frame that we had earlier. And then we are setting the x-axis to be a sequence between 0 and 2. And so what this is going to do is set the x-axis, which is going to be the beta, and the y-axis, which is expected return. And then we're going to graph that and add the point for the portfolio beta that we got in the regression and the expected return that we know that we calculated. And the formula for that expected return that we're going to use for the security market line, so not for the portfolio, but for the line, will be the beta, the x value, multiplied by the average market premium, which is just the mean of the market risk premium, plus the average risk-free rate. So again, that return of the 10-year bond we're using is the risk-free rate, the average of that. And that return of the 10-year bond will be the 10-year bond price divided by 1,200 to make the monthly adjustments. So for each of those periods. And then we're just plotting that down here and annotating the points for the portfolio. For the CAPM regression, we are plotting the market risk premium and the portfolio risk premium. So the portfolio risk premium will go on the y-axis. And this is pretty simple, whether you're doing this in Excel or R, you're just plotting, these variables. And I'm doing it with AES, which is aesthetics. So combining the data into one data frame and then using plot with the data frame as the main argument, and then AES with the X and Y arguments after that. And this is just, I wasn't able to get it to work otherwise, but I think this is just the simplest solution that I had for being able to combine and then graph from the same data frame. So you can play around with that, but this is what I'm using for plotting this. And geom smooth for the regression line. So this will get you a graph that looks like this. So for the dummy regression and seeing whether COVID will be influential in affecting the returns, we are going to create a Jensen alpha object that will be defined as the returns for each month minus the beta times the market return, the market risk premium or the return premium for that month. So this will be each month's return minus this beta adjusted market risk premium. So we want to graph that, and then we want to annotate the points that we are using for our COVID reference. I think this one might be, it extended a little bit longer than this. This is just the old time frame that we were using from 2020, May 1st to September 1st. But I think, if you wanted to update that to be a little bit longer, check the project paper to see which dates exactly we want to use for this. But I'm just going to go ahead and use this, just assume that this is the time frame that COVID is during. So then we can see, right, we have our alpha over time with the COVID and reopen annotations. For the actual calculations of the COVID regression, we're going to follow the same process as previously, right? Set the portfolio risk premium to be the Y variable and the market risk premium times the dummy variable to be the X variable. So the dummy is essentially, that's a value of either 0 or 1, depending on whether the row has satisfied the condition And the condition will be whether it's COVID dates, so whether it's between the date frame that we said before. So just again, assume this is the correct date frame. I think this should be 09. But yeah, so whatever the dates that we use for COVID, it's when it's between those dates, so greater than or equal to May 1st and less than or equal to September 1st. So when we run that regression, the first thing we can see is the p-value of the F statistic. So we can see that that's less than our alpha. So the regression results are significant. If it was greater than the alpha, that it wouldn't be, the whole regression would be not statistically significant. The second observation we can see right at the 95% confidence interval, seeing the change in the market risk premium from before and after. So if it's greater than when you initially ran the regression, you'll know that this dummy variable, this period of time during COVID, actually had an effect on the market risk premium. So in this case, it implied that the market participants needed a higher risk premium during the COVID period, and that checks out with our understanding. It's a riskier period, higher volatility, so you would need higher returns for that risk. And you can also see whether the intercept and the other variables are significant with their p-value. Again, if they're greater than the alpha, they are not significant. The value at risk, we'll start with the portfolio value at risk. We're going to be using the quantile function for this. And we'll set the alpha at 0.05. So this is essentially telling us the VAR 95%. And this is telling us that what percentage we are fairly significant. We are fairly confident that the portfolio will not have a drawdown greater than. So this basically tells us we are 95% confident that the portfolio will not have more than an X amount of drawdown, right? And that would be the value at risk. When we plot it, we can see, right, these are the returns that we're 95% confident will not be exceeded, but we also know that there's a 5% chance of getting these risks. So, this -25, -30% drawdown or whatever, this is the tail risk that is discussed. So it's low likelihood of occurring, but if it does, that's a pretty significant drawdown. So that we want to consider that. So this is the portfolio. You follow the same process. Actually, I did a different process, the market VAR, just to show that there are other ways of doing this. So, if it doesn't work with the type of object that you're using, because I think I was running into that issue before, just experiment with different ways of doing it. So, I still use the quantile, but the plotting is being weird or whatever with the coloring. You can also just use like a line to indicate where the VAR points will start. So to the left of this line, these are all the 5% VAR values. Then we're actually calculating the VAR over here. And as you can see, we have the mean values and the standard deviation values for the various time horizons. So 1 month, 6 month, and 12 months. And the alpha value, which is we'll specify our confidence level, the 5% quantile for the VAR. And then we also have the portfolio VAR and market VAR variables. So we calculate those by applying the calculate VAR function, which will essentially accomplish what we're trying to do, just calculating the VAR. So Once we have all those, we can combine them in a data frame. And we're actually going to use Tidier for this. So if you haven't installed that, make sure to include that. It just makes it easier to, throw things together in a data frame. So here we use function gather, that's from Tidier. So um, this just displays it in a table neatly. So we have the 30-day, the 180-day, the 360-day, various other rows for the portfolio and the market VAR, and the actual values. To graph these, I'm just using ggplot, setting the order levels for the various time horizons, and plotting time horizons and the VARs for the market and the portfolio of assets. Finally, we have the forecasting. The first step, we're going to create a time series object, and then define our testing and our training period. So for that, I just used a cutoff that was about 6 months before the current date, and a start of the testing period that was about a month after the training set end. So this will test the whole winter model for the forecasting. It'll train it in this here, and then test it over here. So we're fitting the naive, the additive, the multiplicative, the simple with these functions, naive, SES, HW, and then just changing seasonal to make it multiplicative or additive. I'm plotting with auto plot so that I can arrange the grid later, but you can just also plot it separately if you prefer. So we're fitting it in the first line, starting it in the testing period, and labeling everything, adding the right colors, the legend, and ultimately we use grid arrange to see these values together. So this is nice. This is essentially just gives us the various forecasting graphs for the naive forecast, the simple exponential smoothing, the whole winter ones. So, the outside of these envelopes will tell us the range of the estimates. The dotted line gives us the actual values, and that middle line, or whether it's squiggly, that's in the same color as the envelope, will tell you the actual line predictions of the various models. So then we always need to check the accuracy. You can do that with accuracy if you have the right package installed. I think forecast is the package that is necessary for this. So if you don't have the package called forecast, make sure to install that as well. But we're making a data frame with all of the statistics and then showing them with this code, the in-sample and out-of-sample accuracy with these. So this will give you the various statistics for the naive, simple, whole winter, additive, and multiplicative, for the out-of-sample and in-sample. And so that's everything you need. So with that, we've completed the code. You can run the whole thing. So this has been the last video on mean variance optimization with a 5-stock portfolio or more. As soon as possible, I will upload a video on doing this in Excel. And in the meantime, if you have any questions, please feel free to reach out via email or put a comment in the comment section. Again, all of the materials that are necessary for this are in the description, so take a look at that, as well as timestamps in the description as well. So leave a like if you enjoyed the video, and I hope this helps your analysis.